Welcome to the deep dive. Today, we're plunging into a challenge that's, well, rapidly becoming essential as large language models become part of our digital lives.
Hmm.
How do we make them truly secure? Specifically, how do we protect LLMs from sophisticated attacks like prompt injection and jailbreaking?
Yeah, these attack vectors are really critical to understand. They represent ways malicious actors can, bypass safety mechanisms
Right.
and potentially force models to leak private data or perform harmful actions or generate stuff they were explicitly designed not to.
And the source material guiding our exploration today is a significant paper that introduces something called JavelinGuard.
JavelinGuard, yeah.
It's presented as a suite of low-cost transformer architectures developed specifically to detect this kind of malicious intent hidden in user prompts.
So our mission in this deep dive is really to unpack these different architectures. We want to understand the thinking behind their design, see how they perform against existing defense methods,
How they stack up, yeah.
and ultimately extract the most important practical insights this research holds for you, the listener.
Okay, let's start by setting the stage a bit. The paper makes a pretty clear distinction between the two main types of attacks we're discussing.
It does.
What exactly are prompt injection and jailbreak attacks in the context of this research?
So the paper defines prompt injection as basically coercing an LLM into performing unintended actions or revealing hidden instructions
How?
by embedding deceptive commands within, seemingly normal input text. The goal is really to trick the model using clever phrasing or context.
Ah, so it's like whispering a secret kind of manipulative instruction into the model's ear through the regular conversation flow.
That's a pretty good way to think about it, yeah. Jailbreaking, on the other hand, is more direct.
More blunt.
Exactly. It involves explicitly trying to override the model's built-in policy constraints or safety alignments. The paper mentions instructions like ignore previous instructions as a prime example.
Right.
It's a sort of explicit defiance of the rules, quite different from the subtle deception of prompt injection.
Okay, so one is deception targeting instructions, the other is direct rule breaking. Why is building effective defenses against these so difficult right now?
Well, the research points out several core struggles for the existing guardrail solutions. They face this difficult balancing act,
Between what?
between achieving high accuracy and maintaining rapid processing speed. Cost is another big factor. Running large, complex checks is expensive. And crucially, many existing methods tend to overfit to the specific attack patterns they've seen during training.
Which makes them vulnerable to new variations, right? Overfitting meaning they get really good at spotting the known attacks but might completely miss something slightly different.
Precisely. And there's also a significant misclassification problem. Many current systems either fail to differentiate between prompt injection and jailbreak attacks.
Or worse.
Or worse, yeah. They incorrectly flag benign user inputs or even just standard toxic content as these specific types of attacks.
The paper showed a really clear example of that mislabeling, didn't it? I think it was in their figure 1.
Yes, Figure 1 illustrates this perfectly. It shows a benign academic prompt taken from a public dataset called WildGuard test.
Okay.
Despite being completely harmless, related to educational content, a typical guardrail using just simple keyword triggers incorrectly labeled it as a jailbreak attempt.
Wow.
Yeah, it really underscores the challenge of building accurate detectors that don't generate a high rate of false alarms. You don't want to block legitimate users.
Okay, that paints the picture clearly. Complex attacks and current defenses have these significant shortcomings in balancing accuracy, speed, cost, and avoiding misclassification.
Right.
This is the problem space JavelinGuard aims to solve. What's their fundamental approach?
So JavelinGuard's core objective is to provide a low-cost, high-performance detection solution that is genuinely practical for deployment, in production environments.
Okay, practical.
Their key insight is leveraging relatively compact transformer variance models, typically around, say, 400 million parameters in size.
Which, I mean, in the world of these multi-billion parameter LLMs we hear about, that's actually quite modest.
It really is. And the benefit of using these smaller models is that they can build accurate, specialized classifiers that achieve extremely rapid inference speeds.
Faster checks.
Much faster. It means they can run detection checks very quickly, even on less powerful or standard CPU hardware.
Which translates directly into lower operational costs, right? Compared to relying on massive LLMs or needing specialized hardware.
Exactly. Lower cost, faster response.
And they didn't just build one model, they developed a whole suite. 5 different transformer-based architectures, each kind of building on the last named after celestial weapons. Let's dig into these 5.
Okay, so they start with Sharanga. This one serves as their foundational baseline.
The starting point.
Right. This architecture takes a standard pre-trained transformer encoder, like ModernBERT, and simply fine-tunes it for classification by adding a single linear layer on top.
Okay, so a very straightforward application of a pretty common technique for text classification. Nothing too fancy yet.
That's right. It uses standard methods like mean pooling or CLS pooling.
Explain those quickly.
Sure, mean pooling averages the information from all the tokens in the input, while CLS pooling uses the representation of a special CLS token as a summary for the whole sequence.
Got it.
And Sharanga employs binary cross-entropy loss, which is a common way to train models to predict one of 2 outcomes in this case, malicious or benign. It's a simple but effective starting point to measure the impact of the later enhancements.
Okay, Sharanga is the basic setup. What's the thinking behind the next architecture, Mahendra? What does it add?
Mahendra enhances Sharanga quite significantly. It refines how the model pools information from the text sequence instead of that simple pooling.
Like mean or CLS?
Right. It introduces an attention-weighted sequence pooling mechanism. This pooling is guided by the CLS token's representation, essentially teaching the model to pay more attention to the parts of the input text that are most relevant for detecting malicious intent.
Ah, so it's getting smarter about where to look in the prompt, not just summarizing everything equally.
Exactly. It learns to spotlight the crucial tokens. Mahendra also uses deeper classification heads attached to the transformer output and incorporates residual connections.
Residual connections, those help with training deeper networks, right? Makes them more stable.
Precisely. They help prevent issues like vanishing gradients and allow the model to learn more complex patterns effectively.
And Mahendra also changes how it handles the errors during training, the loss function.
It does. It uses something called focal loss with a fixed gamma parameter. Now, this is a loss function designed specifically to address the problem of class imbalance.
Which you mentioned is common in security datasets, right? Lots of benign examples, fewer attacks.
Very common. Focal loss puts more training emphasis on the hard-to-classify examples, the tricky ones. This helps the model learn those subtle differences needed to spot clever attacks without getting overwhelmed by all the simple, benign inputs.
Makes sense.
And it's built on a slightly larger backbone, ModernBERT large, adding about 4.8% more parameters than the Sharanga baseline.
Right, so Mahendra builds on the core transformer with smarter pooling, deeper classification, and a more robust loss function for that imbalanced data. What about Vaishnava? The paper describes this as a hybrid neural forest approach. Sounds different.
It is quite different. Vaishnava still uses a transformer encoder, like ModernBERT large, to process the input text and understand its meaning.
Okay, so far so similar.
But instead of attaching a standard neural network classifier at the end, it extracts the summary representation from the CLS token's embedding, just that one vector.
And then what does it do with that embedding?
It feeds that high-dimensional embedding into a classical machine learning model, a random forest classifier.
Random forest.
Yeah.
Interesting.
Yeah. In fact, the paper used 2 separate random forest classifiers. One trained specifically to detect jailbreak, and another one for prompt injection.
So the powerful transformer acts like a sophisticated feature extractor, getting the deep meaning, and then the random forest makes the final call based on those features.
That's exactly it. It's a 2-stage training process.
Yeah.
First, train the transformer, or use a pre-trained one, then train the forest.
What's the benefit here? Why go hybrid?
A key potential benefit compared to those end-to-end deep neural networks is partial interpretability.
Seeing why it made a decision.
Sort of. You can examine the feature importances within the random forest models. It gives you some indication of which aspects of the transformer's embedding were most predictive of an attack. It offers a bit more transparency into why a specific prompt might have been flagged.
Okay, a nod towards interpretability. And Ashwina follows a similar hybrid logic.
It does. Very similar concept. Ashwina is the other hybrid architecture they presented. It uses the same transformer encoder to extract the CLS embedding, but it swaps the random forest classifier for an XGBoost model.
XGBoost, another popular machine learning model. What's the advantage of using XGBoost here instead of random forest?
Well, XGBoost is a powerful gradient boosting algorithm. It's often known for its speed and performance, particularly on structured data like these embeddings. It can be very effective at learning complex interactions between the features extracted by the transformer.
And interpretability.
Similar to random forest, XGBoost also offers partial interpretability through its feature importance scores. So it's another way to potentially get some insight into the decision-making.
Okay, so Vaishnava and Ashwina explore these hybrid models, maybe gaining some interpretability while still leveraging the transformer's power for understanding the text nuances. That brings us to the last one, Raudra, described as their advanced multitask framework. Sounds like the top tier.
Raudra is definitely the most complex, and you could argue the flagship architecture in their suite. It builds upon the foundation laid by Mahendra using that attention-weighted design. But it's fundamentally a multitask model. It shares a single transformer encoder. But here's the key difference. It learns separate token weighting schemes, specifically tailored for detecting jailbreak and prompt injection independently.
Whoa, wait. Separate weighting schemes for each type of attack within the same model.
Yes,
Yeah.
this allows the model to develop highly specialized internal representations and attention patterns. The idea is it gets better at differentiating the, often subtle characteristics of jailbreak attempts versus prompt injection techniques.
That sounds powerful.
And it doesn't stop there. It also features its own dedicated, deeper classification modules, again with skip connections, similar to Mahendra, but for each individual label.
So it has like separate little brains focused on spotting jailbreaks and spotting prompt injections.
That's a decent analogy. It's inherently designed to distinguish between the different categories of malicious input rather than just lumping them all together as bad.
Which seems critical if you want nuanced control.
Exactly. And it uses focal loss again, but with per-task weighting. This makes it robust for multi-class detection and enables it to explicitly learn to differentiate between jailbreak, prompt injection, and benign inputs simultaneously. This targeted approach is something the paper really emphasizes as lacking in many existing solutions.
Fascinating how they built these architectures, layer by layer, adding complexity and capability. So how did they actually put them to the test? What did their experimental setup look like?
They ran extensive evaluations. First, they tested each of their 5 JavelinGuard architectures using different pre-trained transformer encoders as the backbone they mentioned, using ModernBERT, NeoBERT, and EuroBERT.
Why different encoders?
To understand how the classifier design itself performed, sort of independent of the specific underlying transformer variant, does the architecture work well regardless of the base?
Makes sense. And they compared their models against others out there?
Oh, absolutely. They benchmarked their JavelinGuard models against several leading open-source guardrail models that were available. And crucially, they also compared performance and speed against large, proprietary decoder-only LLMs.
Like the big ones.
Yeah, specifically they mentioned GPT-4o and GPT-4.1 mini. This was key to evaluate the trade-off, using massive generative models for this specific security task versus their smaller, dedicated classifiers.
Right, the build versus buy, or maybe specialized versus general purpose argument. What about the data they used for testing? The paper lists, like 9 different adversarial datasets.
They used a really wide battery of tests, included well-known datasets like the NotInject series, BIPIA, Garak, ImprovedLLM, ToxicChat, and WildGuard. Lots of different flavors of attacks and benign text.
And didn't they introduce their own dataset too? JavelinBench?
They did.
And
JavelinBench, tell me more about that. What was the rationale behind creating a whole new benchmark?
So JavelinBench was developed specifically to provide a more robust and reliable evaluation. They really focused on generalization and challenging scenarios. The paper explains it was crafted to include difficult borderline cases and hard negative examples. Hard negatives, what are those?
Prompts that look like they might be malicious, maybe use some suspicious keywords, but are actually benign. They emphasized careful annotation to avoid those mislabeling issues they saw in some existing datasets.
Ah, so it's designed to really stress test a model's ability to differentiate truly subtle malicious intent from just complex or unusual but ultimately harmless inputs.
That's exactly the idea. They also pointed out the significant data imbalance present in many of the public benchmarks. Table 3 in the paper shows this. Some datasets might be entirely benign, like parts of NotInject.
Or entirely malicious.
Like Garak, yeah.
Yeah.
This imbalance is a major challenge for models trying to achieve both a high detection rate for attacks and a really, really low false positive rate on benign inputs. It's easy to get skewed.
Okay, tricky data. Where did the training data for the actual JavelinGuard models come from then?
Their training data was compiled from an aggregation of numerous existing open-source adversarial datasets. But they didn't stop there. They also generated synthetic data.
How?
Using both automated red teaming scripts and, interestingly, manual annotation processes. They specifically targeted edge cases and complex interactions, aiming for a really broad and challenging training corpus to make the models robust.
Okay, a comprehensive setup.
So with all that, what were the key results? What did they find when they ran the experiments? How did JavelinGuard do?
Well, looking at the performance across the benchmarks, Raudra consistently emerged as the strongest performer overall.
The multitask one.
Yep. For instance, Raudra 4.2, which used the ModernBERT large encoder, achieved the highest mean accuracy, averaging around 92.8% across 5 key test sets. Mahendra also showed very robust performance, often doing particularly well on adversarial data and multi-turn conversation data.
How did they fare on false positives? You mentioned that was a big issue for other guardrails, wrongly blocking users. Yeah, false positive rates, FPRs, were definitely a key focus. Sharanga and Mahendra showed pretty stable FPRs, typically ranging from, say, 0.03 to zero point 0.08. The hybrid models, Vaishnava and Ashwina, perhaps thanks to their distinct classification heads, managed to push FPRs even lower on benign datasets, sometimes down around 0.05.
And Raudra.
Raudra, with its multitask design explicitly learning those class boundaries, consistently matched or even improved on these low FPRs, generally falling between 0.03 and 0.06.
That's really low. Crucial for practical deployment, right? You can't be blocking legitimate users all the time.
Absolutely essential. And how well did they do at detecting actual malicious content, say on a dataset like Garak where all the prompts were malicious?
Right, the flip side. On the all-malicious Garak dataset, both Mahendra 1.1 and Raudra 4.2 achieved near-perfect F1 scores. F1 scores, remind me.
F1 balances precision and recall. Basically, how many attacks they caught versus how many benign things they wrongly flagged as attacks. And F1 close to 1.0, which they got, means they caught essentially all the malicious prompts without misclassifying any benign ones within that context.
And how does that compare?
It contrasts pretty sharply with older open-source guardrails mentioned in the paper, which typically plateaued under 0.97 F1 on that set. It indicates the JavelinGuard models were much better at minimizing false negatives, missing real attacks on purely adversarial data.
Okay, strong performance there. What about datasets with more of a mix of content, like BPIA, ToxicChat, and ImprovedLLM?
On those more balanced benchmarks, Raudra and Mahendra generally led the pack again, particularly in metrics like macro F1.
Macro F1 gives equal weight to each class.
Right? Equal weight to performance on benign, jailbreak, and prompt injection. They also consistently showed low false negatives on these mixed sets. The paper attributes this strong performance to the advantages offered by their focal loss implementation, which handles imbalance well, and those attention-based classification heads used in Mahendra and Raudra.
Okay, so strong performance, high accuracy, low false positives, high detection on malicious inputs. But for production, speed is just as vital, maybe more so sometimes.
Absolutely.
What did they find regarding that latency versus accuracy trade-off, especially when comparing JavelinGuard to those huge LLMs like GPT-4o?
This is where the JavelinGuard models really shine and show a significant practical advantage. They are dramatically faster than using large generative models for this specific task.
How much faster?
On their own JavelinBench dataset, Raudra 4.2 and Mahendra 1.1 had average inference latencies around 38 milliseconds. The Ashwina model, the hybrid XGBoost one, was even faster, averaging just 16 milliseconds.
16 milliseconds. Okay, and how did the large LLMs compare on that same benchmark, GPT-4o?
The paper reports GPT-4o had an average latency of approximately 800 milliseconds on JavelinBench.
800 milliseconds versus, say, 38 or 16.
Yeah, that makes the JavelinGuard models somewhere between 20 to 50 times faster.
That is a massive difference for any real-time application. So what's the key takeaway from this speed comparison, especially when you combine it with the accuracy results?
The critical finding, really the bottom line here, is that JavelinGuard models like Raudra 4.2 and Mahendra 1.1 achieved higher accuracy on the JavelinBench, set 96.2% and 94.5% respectively, than GPT-4o did, which scored 91.3%.
Wait, so they were more accurate in orders of magnitude faster?
Exactly. More accurate and much, much faster.
Yeah.
This directly supports their core argument. Small, dedicated, optimized encoder-only models like JavelinGuard are a highly pragmatic and scalable solution for real-time LLM security in production, especially when you need that sub-50 millisecond latency for things like chat moderation or filtering.
Sub-50 meters seems like a reasonable target for real-time interaction.
It often is, yeah.
They also touched on how the speed of these models could help mitigate that loss-in-the-middle problem with really long prompts. Can you explain that connection?
Sure. The lost-in-the-middle phenomenon is where large models sometimes struggle to pay sufficient attention to or retain information from stuff that appears way down in the middle sections of very long input texts. Their attention gets diluted.
Right, I've heard of that.
So a practical mitigation strategy which becomes feasible because the JavelinGuard models are so fast, is to break down extremely long user prompts into smaller, more manageable segments or chunks.
And then run the JavelinGuard check on each segment individually.
Exactly. You process each subprompt independently through the fast JavelinGuard model. This reduces the overall length of text the detection model needs to process in one go, which helps mitigate that attention dilution issue.
And because they're so fast.
Because they're so fast, you can process multiple segments sequentially or even in parallel and still maintain real-time responsiveness for the overall security check on the full original prompt.
That's a really smart way to leverage their speed advantage for a known LLM weakness. Clever. Of course, like any research, this paper acknowledges certain limitations. What were the main ones they highlighted?
Yeah, they're upfront about that. They note the ongoing need for periodic updates to their models. The landscape of adversarial attacks is constantly evolving, right? New techniques will always emerge.
So continuous retraining is necessary.
Definitely. Interpretability also remains somewhat limited, especially in the deeper end-to-end architectures like Raudra. Although they feel the hybrid Vaishnava architecture partially addresses this by allowing inspection of those random forest feature importances.
Any other limitations they mentioned?
They pointed out that depending on the specific domain where an LLM is deployed, think healthcare, finance, legal domain-specific fine-tuning of the JavelinGuard models might be necessary to achieve optimal performance. They need to learn the nuances of that specific type of language.
Makes sense. Tailoring is often needed.
And importantly, they stated that their comparison to the large LLM baselines like GPT-4o didn't involve extensive, prompt engineering on the LLM side.
Ah, so maybe you could make GPT-4o perform better with clever prompts.
It's possible. While skilled prompt engineering could potentially improve the LLM's accuracy on these detection tasks, it would also very likely increase their already significantly higher latency. So there's that trade-off again.
Right. More prompting often means more processing time. Well, this deep dive into the JavelinGuard paper really provides a clear picture of their approach and findings. It feels quite practical.
I think the core takeaway is that this research presents a pretty compelling case for using dedicated, low-cost transformer architectures as a robust, fast, and highly efficient layer of security for LLMs.
Yeah.
By specifically designing models like Raudra and Mahendra for this detection task and optimizing them for speed, they offer a practical solution to those real-world production challenges posed by prompt injection and jailbreak attacks.
And often outperforming much larger models for this specific job while being orders of magnitude faster.
That's the key finding. That insight into optimized, specialized models for security is really crucial for anyone thinking about deploying LLMs at scale.
And looking forward, the future work section of the paper raises an interesting question that kind of builds on all of this. It gets you thinking. Given the constant evolution of adversarial tactics, what does this research suggest about the ongoing need to explore detection techniques that go beyond even these kinds of transformer architectures? Maybe looking at novel models like state space models, or even thinking about advancements in tokenization, how we break text down, just to keep pace and stay ahead in this dynamic landscape of LLM security.
It really does make you consider those foundational layers, doesn't it? How security itself might need to evolve right alongside the LLMs, a constant arms race in a way.
Something for all of us to keep an eye on.